Hello dear friends, welcome back to my YouTube channel Chemistry Aspirant. Now in today's lecture we are going to learn about the formation of molecular orbital energy level diagram for beryllium molecule, or it is also called as a diberyllium molecule. Generally the question asks why the diberyllium molecule or beryllium molecule is unstable in the diatomic state, or simply they will ask you the question, explain the formation of beryllium molecule by molecular orbital theory. So here we are going to consider the 7 simple points by which we can easily explain the formation of beryllium molecule, or we will explain why the beryllium molecule is unstable in the diatomic state. So let's start with this video. So now let us consider the point number first regarding the diberyllium molecule. We know that generally the beryllium molecule is formed by the 2 beryllium atom, and each beryllium atom in the ground state has a 4 electron in its 1s and 2s atomic orbitals. I have shown the electronic configuration of the beryllium atom here. We know that beryllium atomic number 4 and its electronic configuration will be 1s2 and 2s2. So this is our point number first. Now the point number second, which is regarding the calculation of a total electrons in the diberyllium molecule. Now we know that diberyllium molecule is formed by the 2 beryllium atom, and each beryllium atom contains the 4 electron. Hence your beryllium molecule or your diberyllium molecule consists of totally 8 electrons, which is we are going to distribute in the molecular orbital of your diberyllium. Now, let us consider the third point, that is the construction of molecular orbital energy level diagram for diberyllium molecule. We know that the linear combination of 2 1s and 2 2s atomic orbital of each beryllium atom gives the 4 molecular orbitals. Now out of that 4 molecular orbitals, the 2 are the bonding molecular orbital, that is sigma 1s and sigma 2s, while the remaining 2 molecular orbitals are actually called as an anti-bonding molecular orbital, and they are represented by sigma star 1s and sigma star 2s. So the total 8 electrons are distributed in these 4 molecular orbital, that is the bonding molecular orbital and the anti-bonding molecular orbital, by following the Abou's principle, Pauli's exclusion principle and Hund's rule. So here you can observe that out of the 8 electron, the first 2 electron will enter into the sigma 1s bonding molecular orbital. So out of 8 we already distributed the 2 electron, the 6 electron is remaining. Again out of 6 electron, again the 2 electrons will enter sigma star 1s anti-bonding molecular orbital. So again out of the 6, the 2 is distributed in the sigma star 1s, so only 4 is remaining. So out of that 4 electrons, the 2 are again enter into the bonding molecular orbital, that is your sigma 2s bonding molecular orbital. So here only 2 electrons is remaining, and that last 2 electrons will enter into the anti-bonding molecular orbital, that is sigma star 2s anti-bonding molecular orbital. So we have distributed the 8 electrons. I have shown this in this animated form 1 by following all the 3 important principles, Abou's principle, Pauli's exclusion principle and Hund's rule. As a result, we get the molecular orbital energy level diagram for this diberyllium molecule. So this is your point number 3. Now the next point, point number 4, that is the electronic configuration of diberyllium molecule. So here I have shown the electronic configuration for diberyllium molecule. So electronic configuration can be written as a kk constant, that is sigma 1s2, comma sigma star 1s2, comma sigma 2s2 comma sigma star 2s2. So you can observe that I have distributed these 8 electrons in the 4 molecular orbital. So for writing this electronic configuration, you can take the reference of the point number 3 also that I have shown here, and you can easily write the electronic configuration by just observing the molecular orbital energy level diagram for this molecule 1. So I have shown this simple electronic configuration here one. So this is about the electronic configuration for your diberyllium molecule. Now the next, that is your step number 5th. So here we are going to calculate the bond order for diberyllium molecule. Generally the bond order is given by the formula bond order equals to 1 by 2 into Nb minus Na, where Nb is the total number of electrons in the bonding molecular orbital, while Na is the total number of electron in the anti-bonding molecular orbital. Now for your beryllium molecule, here we know that the sigma 1s and sigma 2s contain totally the 2 plus 2, that is the 4 electron. So therefore the value of Nb will be equals to 4. Again we know that Na, that is the anti-bonding molecular orbital, we know that sigma star 1s and sigma star 2s contain the 2 electrons. So total there will be again the 4 electron, therefore the value of Na also will be equals to 4. Bond order equals to 1 by 2 into Nb minus Na, therefore bond order equals to 1 by 2 into 4 minus 4, that will be equals to 0, and after the simple mathematical calculations the bond order is equals to 0. So from the bond order there is a no bond between the two beryllium atom. And now the last point, that is the stability of the diberyllium molecule. So at the start we already seen the question, that is generally the diberyllium molecule is unstable. Why? So we will find the answer of this question in this point. We know that generally the stability of the molecule depends upon the two important factors. Now the first factor is the number of bonding electron and anti-bonding electron, and the second factor is the bond order. So here you can observe that generally the number of bonding electron and anti-bonding electrons are equal, that is the value of Nb is equals to the value of Na, and we observe that the bond order is a 0. It is always unstable, and as the bond order is a 0, hence we can say that the beryllium can be present only in the monoatomic state. So in this video you have learned the simple 6 to 7 points by which we can easily explain why the beryllium is unstable in the diatomic state. Hope you will like this video. Thank you so much for watching this video. See you in my next video.